Thanks for attending another of my video lectures. You may have viewed my earlier video, Trusses, Electrical Circuits and Kirchhoff's Laws, and thought that it was of some academic interest but not of much practical use. In this video, I hope to convince you otherwise. If you are a student of engineering or applied mathematics, you may have had to learn the force method for indeterminate trusses. In this video, we take a problem that has been solved on YouTube by the force method and solve it by the method of Stroops. You are urged to view the video with the force method and this one and compare the two approaches. My name is Charles DeMattas. I am a retired lecturer from the University of the West Indies, St. Augustine campus, Trinidad. The university supports my video creation by providing me with a workspace and other benefits. I hope that this video comes up to the standards worthy of the university's sponsorship. So I've taken a problem from this video, Analysis of Indeterminate Truss, Problem 1, Structural Analysis. So you can view this video to see the solution by the force method. Okay, and you can compare it with the solution that will be given in this video. Basically, you have a truss A, B, C, D, which is basically square, 4 meters by 4 meters, and you have 6 members. It's hinged at C. The support here does not allow movement horizontally or vertically, only rotation is possible, and at D it's on rollers. So this is internally indeterminate, but externally it's determinate. All members have the same L over AE value. We will analyze this using the method of Stroops, which is developed in my video, Trusses, Electrical Circuits, and Kirchhoff's Laws. So I invite you to view this video also to obtain an idea of the method of Stroops. First of all, we will do transmission of external forces to the supports. So the only load is the 5 kilonewtons vertically downward at B. Now this will go straight to the support at D through this member BD. So the force in BD will be compressive of value 5. For compression, we denote it by a negative value, so it's negative 5. So this is our compressive force in the member BD. All of the other members have 0 force in them. Now we will introduce our Stroop forces. From my earlier video, Trusses, Electrical Circuits, and Kirchhoff's Laws, you would have learned that this type of structure, ABCD, which is rectangular and 6 members, is a Stroop. A Stroop is a minimally indeterminate structure. And these are the Stroop forces, which you would also have learned about in that video. We have F on the perimeter and minus F times square root of 2 on the diagonals. Now I have not drawn arrows here to indicate the direction of the forces. This is because the F can either be positive or negative. Just remember, a positive force indicates tension, a negative value of a force indicates compression. So the F here, depending on whether it's positive or negative, can mean a tensile or a compressive force. So no arrows are drawn to indicate the direction of the forces here. Now we superpose the previous two diagrams into one. Okay, we add the forces that transmit the loads to the supports and the Stroop forces. So just remember that in transmitting the load to the support, you had a -5 here plus the Stroop force F. On all of the other members, you had 0 for the first diagram, and when you add that to the Stroop forces, you just get the Stroop forces on the other members. So these are what I call the superposed forces. Once we have obtained the combined forces, those superposed forces, we can write down the compatibility equation. Now, we've seen this type of Stroop in my earlier video on trusses and Kirchhoff's laws, and we obtained the compatibility equation for this type of Stroop. So I'm just writing down the form of the compatibility equation here. So it's a summation of terms. The terms are of this form: the length of the member squared times the force in the member over the area of the member. I should really have a E in the diagonal for each member, but assuming all of the members are made of the same material and the E's are the same, I just factor them out and cancel. So I'm just writing the A in the denominators here. And you can try to memorize the compatibility equation as a formula, but if you look at the form, you'll see it is of this form. It's the summation of these terms around the perimeter equated to the summation on the diagonals. So if you remember this form, you'd be okay. I tried to avoid minus signs, which would be obtained if I carried across here, put everything on one side equal to 0. But I'm trying to not use too many minus signs because it can be confusing. The F's could either be positive or negative, and it's very easy to make an error with the signs. Now, the initial statement of the problem had this assumption that the L over AE is the same for each member, and then from each term here we can factor out an L over A. The E's are constant, so we just need to factor out L over A from each term, cancel those, and we would get the compatibility equation in this form: summation of LF equals summation of LF, perimeter here, diagonals here. So the coefficients of the forces are just the relative lengths of the members. We don't have to use absolute lengths, of course. We can factor out and bring it down to a relative length. So these are the coefficients, assuming L over AE for all members. You can think of the length of this member as a unit. So this is 1, 1, 1, 1, and then you have square root of 2 on the diagonals. Again, just using relative lengths. So here I've put together previous two slides, A, B, C, D. These are the coefficients for all the members. Here are the superposed forces. Notice F minus 5 here. Superposed forces for all the members. And what we are going to do is multiply the coefficients times the corresponding force and add those along the perimeter. So it's 1 times F, 1 times F, 1 times F, 1 times F minus 5. That's the sum on the perimeter. On the diagonals you have root 2 times minus F root 2, which is minus F root 2 squared, and similarly here root 2 times minus F root 2, similar term here. So this is our compatibility equation. Now in the force method and other methods, you often make a table. You list the members and then the lengths, and then you list the forces and the extensions and whatever. But I prefer not to make up a table. I just prefer to put the information on a diagram and just use the diagram, so I know which coefficient corresponds to which force, and then I can do the multiplication easily with the two diagrams and obtain the compatibility equation. So this is the equation from the previous slide. You can square these, get rid of the square roots, and the right hand side reduces to minus 4f. The left hand side is 4f minus 5, and this becomes 8f equal to 5, and f is equal to 5 over 8. So once you have obtained f, you can substitute into the diagram with the combined forces, with the superposed forces, and you will get the forces as follows. So it's 5 over 8 here, minus 35 over 8 here, 5 over 8, and so on. So notice here that I've put in the arrows here also to indicate the direction of the forces. Positive force, of course, indicates tension. Negative force indicates compression. So you have compression on the diagonals here also. So these are exact values. Notice I've written the square root of 2 here, and I can write the decimal form also. So this is the solution in decimal form, 0.625 minus 4.375, etc., etc. And you can compare this with the solution given in the video, which uses the force method. You'd find that these are the same values. So here I've shown that my method of Stroops gives the same values, gives the same solution as the force method. So you can decide which of these you think is better for you, whether you prefer using the force method, where you have to calculate all of the member elongations and multiply by the lengths and so on. Or you can think of using my method of Stroops, which gives the same result. So I ask you to compare these methods. Before we go ahead, I just want to mention that there was one external load here, 5 kilonewtons here, and here we see in the member BD the compressive force is a little less, 4.375. so what happens is that this 5 kilonewton is distributed to other members, to other parts of the truss also. So it is a slight reduction in the compressive force in the member BD. But of course, you also have compressive forces along the diagonals here. So this is one of the effects of the indeterminate structure. You have, notice the compressive force here is 0.884, which is a little more than half kilonewton. Right, I will talk about this a little later, but you can of course end right here, because I've illustrated, I've done what I set out to do. I've set out to show that my method, the method of Stroops, gives the same results as the force method, and you can decide which method you understand better and which one you think is easier to apply, and which one you think is the computations are easier to perform. Right, so I'm not going to try to influence you too much, but I just want to illustrate my method of Stroops in this video. So what I'm going to do next, if you are willing, you can stop here, and because you can ignore the rest of this video if you like, but I'll just tell you that in the remainder I'm going to give some extras which are not on the video on the force method. So I'll give some extra a little extra detail on the analysis of this truss in the remaining slides. So extra 1, this is the first extra. Now, in the assumption we made initially was that you had a constant L over AE, but suppose we instead had the member cross-sectional areas being the same. All of the members have the same cross-sectional area. How would that change the analysis? Well, in that case, the compatibility equation, which can be written in this form, would reduce to this form, because the areas are all equal. So in each term we can take out 1 over the area as a common factor and cancel on both sides, and the compatibility equation would reduce to this form. So you can see here the coefficients are the squares of the member lengths, not just the member lengths as we had before, but the squares. So these are the coefficients. Notice you have the 1s, which is 1 squared on the perimeter, and you have 2 on the diagonal. That's the square of root 2. So the compatibility equation using the 2 instead of the square root of 2 would be this. These are the coefficients times the same combined forces as we had before. We get this compatibility equation. Simplify this, you get minus 4 square root of 2f, The right hand side again is 4f minus 5, and this is equivalent to 4 into 1 plus root 2 f equal to 5, or f equal to 5 into this divided by 4. So again we obtained an exact value for f. And here is the solution for this value of f. I've gone straight to the decimal form. Notice here it's minus 4.482. You can compare it with the solution in the first case where L over AE is constant. The compressive forces on the diagonals 0.732, again above 0.5 kilonewtons, and again this compressive force slightly below the 5 kilonewton external force. This is another extra that I will give you. If the members have the same weight or volume, because they're made of the same material, to have the same weight they would have the same volume. So the cross-sectional area times the length would be the same for all members. And this is the standard compatibility equation. What I do, I multiply above and below by the length of the member. So it's L cubed over AL, L cubed over AL. Now if AL is the same for all of the members, you can cancel all of these AL and the ALs from the denominators. And then the compatibility equation reduces to this form. Summation of L cubed times F equal to the summation of L cubed times F. So again, here the coefficients are the cubes of the lengths of the diagonals. So these are the coefficients, assuming that each member has the same weight. So we don't want the diagonals to be any heavier than the members on the perimeter. These would be the coefficients that we would use. Okay, so this is root 2 cubed on the diagonals and just 1 cubed on the perimeter. So again, we can write the compatibility equation again using the same coefficients 1, 1, 1, 1, and then 2 root 2 and 2 root 2 for the diagonals. I think it should be, oh okay, here. So here I've taken the minus sign outside. No, usually I would have written this plus and the minus inside, but I've taken it outside right away. Anyway, this gives you minus 8f on the right hand side, same 4f minus 5 on the left hand side, which is 12f equal to 5, or f equal to 5 over 12. So once I have these, I can substitute f into the diagram with the combined forces, and I will get the forces as follows. Here I've gone straight to the decimal form. Notice compression here minus 4.583. On the diagonals, the compressive force is minus 0.589. Again, it's a little bit closer to 0.5 kilonewtons, and you have tensile force here, tensile force here, tensile force at the bottom, these three being equal. In the previous cases, the compressive force in the diagonals were greater than 0.5 kilonewtons. But suppose the diagonals were made slender with a buckling force of 0.5 kilonewtons. Then when the load is applied, the diagonals would buckle as soon as they reached 0.5 kilonewtons in compression. Even after buckling has occurred, there is still equilibrium at each joint. So the forces on the superposed force diagram are still valid. We can obtain F that will give us diagonal forces of minus 0.5 kilonewtons, and then that F can be used to find the forces in all the other members, and this is what we've calculated here. So these forces are in equilibrium given that the diagonal forces are minus 0.5 kilonewton. Of course, you have external force at B and at D. Buckled members can have their lengths greatly reduced. If two members buckle, then the structure can become a mechanism. So, for example, these diagonal members have the same forces, so they would buckle at the same time. And in such a situation, the structure can become a mechanism, which means it behaves as if there were no diagonals. It would deform into a parallelogram shape. There are two limiting forms when B moves to the right or to the left, and between those two extremes the forces again would be in equilibrium and the structure would satisfy equilibrium conditions. Now at the extreme right for B, this member BC would be at its maximum buckle length. That is, when it is still straight with no curvature and the buckling has just started. So the buckling has just started at the 0.5 kilonewton force value. So it's just axial compression in force there. That's when B is at the extreme right. And when B is at the extreme left, A would also be at its extreme left, which means the diagonal AD would be at its maximum length. That is when buckling has just occurred, when there's only a compressive force of 0.5 kilonewtons and the member is still uncurved. So you can take the buckling into account when you are designing this type of structure with slender diagonals. You can, once you know the elongation of the members for these forces, you can calculate the distance B would move to the right or to the left, within which there is still equilibrium possible, and you can decide whether that those displacements for B are allowable in some sense of the word. So you can design for compressive forces in these members that create buckling, and treat that as a limiting state, and see whether the horizontal movements of B are permissible. When you are designing a determinate structure, you can obtain the forces in the members purely from the equilibrium conditions, and then you can design the member properties to be able to cope with those forces. For a determinate structure, you have to make assumptions about the areas of cross-section of the members, and this is what we did previously. We made various assumptions. In one case, we assumed all of the cross-sectional areas were the same. In another case, we assumed L over AE was the same for all members, and so on. But once you make those assumptions and you obtain the forces in the members, you then go and design and check. You check the cross-sectional areas, the second moments, etc., to make sure they are adequate. If they are not adequate, you use different cross-sectional properties. Now, if you change the cross-sectional properties of the members, then you have to go and analyze the structure again, and with the new cross-sectional areas, the forces may change, and then you have to go back and check for those new forces and redesign possibly and repeat the process. So what we will try to do now is to reduce the effect of changing the cross-sectional areas on the forces in the members, and we try to use the compatibility equation to help in the design of the truss. So we'll use this not just to find the forces in the members, but also in the design of the cross-sectional areas of the members. Let's suppose the cross-sectional areas of the members were as follows. So we have again A, B, C, D is our truss. Let's suppose the top and bottom have the same cross-sectional areas, A1. The left and right verticals have the same cross-sectional areas, A2. The diagonals have the same cross-sectional areas, A3. Then the coefficients of the compatibility equation would be these values. Okay, remember it's the length squared over the cross-sectional area, assuming all of the members are made of the same material. I'm using the relative lengths here, 1, 1, 1, 1 on the perimeter, and the length, the square root of 2 squared will be just 2 on the diagonals, and everything is over the respective cross-sectional areas, A1, A1, A2, A2, A3, A3. So these are the coefficients in this situation. So here we have the coefficients and the superposed forces. As we had previously, we only have one load case with the 5 kilonewtons at B. And then we can simply write down the compatibility equation. Remember, it's the coefficient times the force, coefficient times force. On the perimeter, you have these terms, okay, F over A1 and F over A2, that's the top and bottom members. And for the left and right sides, F over A2 here and F minus 5 over A2. On the diagonals, it's 2 over A3 times minus F over root 2 plus the same term here. And we can go forward with that. Alright, so I've brought this across from the previous slide. I've carried over the 4 root 2F over A3 here. I still have these two terms in A2. What I will do is put these terms in A2 on the right hand side, so it becomes 2F over A1, this over A3, this over A2. Now if we wanted F equal to 1, alright, so here I am putting in the value of F. Not making any, I'm not using this to calculate F because I'm just using arbitrary variables for A1, A2, A3. Suppose we wanted the F to come out to be 1, then replace F by 1 in the numerators here. You will get these values, and then multiply by A2 across here and divide by 3, multiply by A2 over 3 right through, and you will get this equation, A2 over A1 over 3 over 2 plus this term over 3 over 4 root 2 equal to 1. Okay, so let's continue here. F equal to 1. This is the equation we obtained on the previous slide. Notice that the A's are all positive quantities and the denominators, of course, are positive quantities, and this is equal to 1. So here the A2 over A3 must be less than the denominator 3 over 4A2. Why is that? Because if the numerator here were greater than the denominator, this would be greater than 1, which means that this term would have to be negative for the sum to be equal to 1, but you cannot have this being negative, so you must have a smaller numerator here than its denominator. And of course 3 over 4 root 2, this is less than 1 also, so it shows that the A2 is less than the A3, and we do not want this in our design. Suppose we do not want this in our design. A2, remember, are the areas on the left and right vertical members, and A3 is the area of cross section on the diagonal. So we don't want the diagonal members to have greater cross-sectional areas than these vertical side members. So this situation with F equal to 1 is not desirable. So let's try a different value. Let's try F equal to 1/2. Then put that in the equation on the previous slide. We will get put that into this equation which we obtained on the previous slide. But F equal to 1, we'll get 1 over A1 plus 2 root 2 over A3 equal to this. And again we will multiply by A4 over 4. Alright, so this is the equation we obtained previously. We multiply by A4 over 4. Right hand side becomes 1, and then we will get A2 over A1 over 4 here, plus A2 over A3 over root 2. So here we have two positive terms summing to 1. Notice if you think of this as a variable and this as a variable, if you plot this variable against this variable, you obtain a straight line. Okay, the intercepts of course will be 4 on this axis and square root of 2 on the other axis. So let's look at that. Right, so here we are plotting A2 over A3 against A2 over A1. So these values that satisfy the equation will lie on this straight line. This line goes through 4 on one axis and square root of 2 on the other axis as before. Now what you want to do is you want to find relative cross-sectional areas, A1 over A2 over A1 and A2 over A3. A2 and A3 are cross-sectional areas on the horizontal top and bottom and the vertical left and right members. So you would like A2 over A3, you would like these to be more or less equal, in other words close to 1, either a little greater than 1 or a little less than 1. Now what about the A2 over A3? You would want the A2 to be greater than the A3. Remember, A3 is the diagonal member. You want the diagonal member to be smaller than the member on the perimeter. So you want this ratio to be a little greater than 1, somewhat greater than 1. So a point like this on the diagram would be okay for us. Okay, so we would like the A2 over A3 to be a little greater than 1. So the A3 here is smaller. And this is okay also for the A2 over A1 to be a little less than 1, about a little less than 1. So the A2 is less than the A1. This would be a satisfactory design from our point of view. Okay, of course you can use various points on the line. I'm just picking one that is suitable for our purposes here. Okay, so this will give us an adequate design, and we've chosen here f to be 0.5, okay, which is a value of f I think we looked at before. And once you do this, you can you know the forces basically. Once you know these ratios, you can look up your tables of sections, cross-sectional areas of your standard tables or steel with steel sections, and obtain sections in these ratios, and you can design using this. And you've already chosen the F, so you know what the forces in the members will be, and you can go ahead with a design like that. Okay, so I'm just showing you here how the compatibility equations can be used in design also, not just in the analysis of the truss. Once again, I am indebted to the University of the West Indies for support in my video creation, and I hope my videos will be of use to persons studying structural analysis and designing trusses. So I again ask you to compare the force method and the method of Stroops that I have developed. Leave comments in the comment section telling me which method you prefer, and you can suggest other problems where I can give a comparison between the two methods, method of Stroops and the force method. So I appreciate your contribution, your comments, and you can like and share this video also. Thank you very much for your attendance.